All right, we're going to go ahead and get started. It's a quick turnaround with the break, so I'm sure we're going to have people trickling in over the next couple minutes. But we want to start by thanking everyone for joining us today. We have a couple more announcements as everyone joins. First, we're recording this session and it will be available in Whova, our conference app, within 2 weeks after the Congress ends. If you'd like to ask our speakers any questions during the session, please use the Q&A area to the right of your screen. The chat window is also where you can engage with other attendees. And we kindly ask that you keep your mics and cameras off during the presentations and follow the presenters' leads on when to engage with cameras and microphones on. We are ready to get started, so I am going to hand it over to our speakers to begin. Over to you, Louise.
Thanks, Emma. Yeah, this is the second part of our session, Fire in Southern Appalachians, Past, Present, and Future Resilience. I'm going to go ahead and just get it started here. Will Flatley. This is a recorded presentation, but he is here. So if you want to ask questions, again, you can put it in the Q&A in Whova. And if you are a speaker, you can also voice your question. But yeah, Will Flatley is an assistant professor at University of Central Kansas.
Hello, my name is Will Flatley, and I'm going to be presenting on some work by myself and my co-author, Charles Lafon, examining the tree ring record from the Appalachian Mountains for evidence of high severity fire in the past. And so this work is relevant to this session's theme on the 2016 fires in Gatlinburg, because we're interested in knowing whether this fire was exceptional. How common was high severity fire in the past in these forests, and how much of a role should we expect to play in the future? And so we know from tree ring reconstructions of fire history that fires burned frequently in these landscapes for at least 200 years prior to fire protection in the 20th century. Moreover, there are many plants in this region that thrive following high severity fire, and their presence in the landscapes gives us some indication that high severity fire has played a role in these landscapes for long time scales. So we typically think of tree ring fire history reconstructions as evidence of low severity surface fires, but there is often evidence of high severity fire in fire history charts as well. For example, this is a fire chart from Linville Mountain in North Carolina. And so just to explain what's going on here, each of these horizontal lines is an individual tree, and you can see the dates that their rings span down here on the bottom. And then the vertical lines are fire scars recorded on those trees. And then these similar but smaller vertical lines at the start of these tree records are pith dates, or establishment dates of those particular trees. And so in a fire chart, we can look for clusters of these pith dates that indicate a cohort of trees established around the same time, potentially in response to high severity fire that opened the canopy and created high light conditions for the establishment of shade intolerant pines. Interestingly, this site at Linville Mountain has experienced several fires in recent decades, with some large areas of high severity fire. And so you can see Charles here standing in one of these areas that experienced high severity fire, and he's right there in the middle of a cohort of pitch pine that established following a fire in 2000. And so we're not the first ecologists to note the presence of cohorts in the age structure of pines in the Appalachians. Charles Williams previously noted these cohorts of establishment in the age structure of Table Mountain pines in the Appalachians. And his theory to of the origin of these cohorts was that they were the product of the industrial logging era at the turn of the 20th century, when these stands were logged, slash was left on the sites, and then often burned at high severity. And his view is that these cohorts were mainly the product of these high severity fires at the turn of the century. However, as you can see in this fire chart and many of the other fire charts that we've developed, there are cohorts that precede or that established prior to that industrial era in the 1800s and even going back into the 1700s. So that leads us to our research questions. And number one is there evidence of high severity fire occurring in the past in yellow pine stands from the central and southern Appalachian mountains? Research question two, did these cohorts mainly establish following the industrial logging era as proposed by Williams? And third, what was the past frequency of high severity fires in these stands? Okay, so this is our study landscape. We included 14 fire history sites that were developed by myself and Charles, and then several collaborators through the years. The sites can be subdivided into two regions. So the Central Appalachians in Virginia that included 8 of these sites, and the Southern Appalachians in Tennessee and North Carolina that included 6 sites. And 4 of those 6 sites in the Southern Appalachians were within Great Smoky Mountains National Park, obviously very close or adjacent to Gatlinburg. Okay, so methods. For this project, we used fire-scarred trees, snags, stumps, and logs from these 14 sites. And the wood was collected and cross-dated for fire history reconstructions using standard dendrochronology methods, which I won't get into in this talk. But then we selected samples that included an intact pith, so we could determine that establishment date. And we grouped these trees into decadal establishment bins. We were able to date the pith to a single year. However, these samples were often cut at different heights to retrieve the best scar surface for fire history analysis. And there's a lot of uncertainty in the time that it takes trees to reach a particular height. And so we felt that decadal bins were sufficiently coarse to account for this uncertainty with the establishment dates, while still being meaningful in differentiating different high severity events and providing useful data on the frequency of these cohorts and the high severity fire that they likely are the product of. Okay, and so we then took these decadal counts of tree establishment and we used them to identify cohorts, which we determined as any decade with a 50% increase in establishment from the previous decade, and with at least 4 trees establishing during that decade. So these red bars show establishment that would have met that threshold of a cohort. We also chose to restrict our time window of analysis to the period from 1830 to 1930. Most of the reconstructions stretch back into the 1700s or earlier, but the records suffer from reduced sample depth in these earlier periods. So to reduce the likelihood that we were missing cohorts due to smaller sample size in the early record, we started analysis in 1830 at all sites when they have a reasonable number of samples available at all sites. We then ended the analysis in 1930 in order to avoid any effect of fire protection. And this window also had the benefit of falling completely within the post-Euro-American settlement period at all of the sites, and obviously prior to that fire protection period. Okay, so results first, just the overall fire regime and fire history. This is a composite record of fire from each of these different sites. And so you can see obviously a lot of fire in these landscapes prior to the fire protection period, or the onset of fire protection period. And so if you look at all sites, the average composite mean fire interval was 3.2 years. And then there was a slight difference between the Southern and Central Appalachians, with slightly more frequent fire in the Southern Appalachians at a 2.5 year fire return interval versus 3.6 years in the Central Appalachians. And the fires are mostly dormant season scars, which means that they occurred outside of the growing season, sometime between the late fall and early spring. And interestingly, this seasonality matches with the Gatlinburg fires that occurred in December of 2016. Okay, so looking at the cohort record. And so most of the sites exhibited cohorts during the 100-year record that we analyzed. And this is showing just the percentage of sites that did record cohorts during that period. So 71.4% across all the sites. And then we do see some difference between the Southern and Central Appalachians, with only 50% of sites in the Southern Appalachians recording cohorts versus 87.5% in the Central Appalachians. And then from that, we can calculate a mean cohort interval, just as we would calculate a mean fire return interval using fire scars. And this can really be viewed as a proxy for the mean high severity fire return interval. And so overall, that interval of cohorts is 107.6 years for all sites. And then again, a difference between the Southern and Central Appalachians, with more cohorts recorded in the Central Appalachians and an 88.9 year mean return interval versus 150 years in the Southern Appalachians. And then finally, looking at this diagram over here, thinking about temporal alignment of these cohorts. So was it perhaps climate, broad scale climate, that was driving these high severity fires? It's difficult with such a small sample to really conclude anything. Perhaps there is a little bit of temporal alignment, with the Central Appalachians having more cohorts in kind of like the middle of the record. But again, it's a pretty small sample size to draw any conclusions. Okay, so discussion. Well, cohorts were detected at most of these sites, suggesting that high severity fire played a role in the fire regime and ecology of these stands at a frequency of about every 100 years, slightly more frequently in the Appalachians and less frequently in the Southern Appalachians. We can also clearly say these cohorts are not an industrial artifact. They did not just occur following the industrial logging era, but we demonstrate that they were occurring with some frequency during the 1800s. And we can see that they were occurring in the 1700s prior to Euro-American settlement. We just didn't feel confident in calculating an interval, since it seems likely that this early record is incomplete. So I said before, it appears that high severity fire may have occurred at greater frequency in the drier Central Appalachians. And so this may be because the Central Appalachians have more windows of drought and fire weather conducive to high severity fire compared to the wetter Southern Appalachians. And this also seems to indicate that it was likely fire weather rather than fuel accumulation that was driving these high severity events. And we can say this just in knowing that fires were burning frequently in these stands throughout this period of analysis in the 1800s, with these mean fire intervals from 2 to 5 years. And frequent fire in these stands should have kept fuel loads relatively low, suggesting that it was not an issue of fuel accumulation, and also indicating that prescribed burning and fuel reduction may not prevent these fires from occurring in the future. Okay, a couple limitations of the study. So one limitation is that these cohorts are imperfect recorders of high severity fire. So there are other disturbances that could have initiated these cohorts, like insect outbreaks, or there could have been shifts in climate that resulted in cohorts of establishment, or longer gaps in the fire interval that enabled trees to establish. However, one way to address this with additional analysis would be look for growth releases in trees that survived through these fires, and look and see if there were growth releases. That would indicate that it was, at the very least, a disturbance that opened the canopy that created conditions for the establishment of these cohorts. And then a second limitation is that we did not use a systematic sampling protocol, as we were opportunistically collecting samples with fire scars. And so this means that there could be biases or that we are missing cohorts in these samples. So these are drawbacks. We feel that the information is still valuable because it is some of the only information that we have on the frequency of high severity fires in the past. And we can also use these limitations to guide future efforts to look at the tree ring record and high severity fire in cohorts. And so one strategy would be to do a systematic sampling of all stumps across a large landscape. And so not just targeting the fire scarred stumps, but basically collecting all of the material that we could use to glean establishment dates. And this would have the advantage of increasing the sample depth in the early record. And so we might be able to then go back into the early, into the 1700s and look at the presence of these cohorts and how frequently they were occurring in the period prior to Euro-American settlement. And then looking at a larger landscape, collecting more wood would also allow us to potentially calculate the extent of high severity effects and look at whether these were burning across multiple independent stands along ridges or along separate ridges. So for example, in this fire chart, we can see that 2 of the stands have clear evidence of these cohorts, and then 2 of them don't. And so you can start to look at that spatially and start to think about how much area is being impacted by high severity fire and how large these high severity effects were. Okay, so I'll just finish by saying thank you to all of the colleagues that helped develop these fire history reconstructions. And then also thank the Joint Fire Science Program, which provided the funding for the original fire history research, which is what this study was based on. So thank you very much, and I'll take questions.
All right, and here I am live in person for questions.
Thanks, Will. That was great. Again, it is very quiet in the chat room and in the question and answer. What about some of the speakers? Do you guys have a question for Will?
I do.
Yeah, absolutely.
Yeah, Will, thanks for the presentation. Good stuff there. And I'm really curious, with fires so frequent, it seems like you must have some of those yellow pine stands that develop with a stand replacing fire and come back as a cohort, but then experience multiple low or moderate severity fires after they've developed. And I was wondering how much evidence you've seen for that. And then second, I was just wondering if you've been able to dig into any climate data and look at how some of those higher severity fires might line up with droughts and things like that.
Yeah, so thanks, Matt. And good question. So one, just with the high severity fire and then producing cohorts and then potentially frequent fire following, you do see some evidence if you just compare the age structure from one site to another. And so some of them, like that, the Linville Gorge site that we know today or recently has experienced high severity fire, you see real clear cohorts. And then there are other sites where it's more continual recruitment of pines. And so we sort of interpreted that as slightly differing fire regimes where you have continual recruitment with more frequent fire and maybe establishment in areas that don't burn in particular years or during a little bit longer years. And then maybe less frequent, but higher severity fire producing those cohorts. And then, well, oh yeah, and then climate. So the the challenging thing about, and I'd love to examine climate, you've got to look pretty coarsely because, because of the uncertainty with the establishment dates that, and binning them by decade. So you'd have to look at maybe, decadal climate, but you really can't start comparing it to, let's say, annual reconstructions of PDSI.
Gotcha. Great. Thanks. I appreciate it.
Yeah.
Great, thanks, Will. I think we'll move on to the next speaker now. So this is a pre-recorded presentation. The subject is originally, the lead speaker is Yongqiang Liu. He's a research meteorologist with the Forest Service here in the Southern Research Station in Athens. And his colleague, who they're both colleagues of mine, Marcus Williams, did this pre-recording for Yong. So that is what it is. But neither of them are on today. So unfortunately, they cannot answer questions, but you can always email them or contact them through the conference website. Thanks.
Hi, my name is Marcus Williams. Today I'll be presenting on behalf of my colleague, Yongqiang Liu. Presentation will be on the air quality impact of duff burning from the 2016 Appalachian wildfire. Wildfire emissions have various impacts on health and air quality. Those emissions include carbon monoxide, fine particulate matter, which will be known as PM 2.5, nitrogen oxide, volatile organic compounds, VOCs, and nitrogen oxide and VOCs are a major precursor for ozone production, which is also something that's hazardous to health and air quality. As I mentioned before, fire emissions have an impact on air quality. Fires contribute about 27.5% of the U.S. total PM 2.5 emissions. Fires also contribute 26.9% of volatile organic compound emissions, and wildfires produce about 3.5% of global tropospheric ozone production. I will briefly introduce some of the burning phases found during fire. First is the flaming phase. High temperatures and visible flames. Normally these fires burn within 1 day. And there's also significant smoke, plume rise, and smoke transport. You also have the smoldering phase. Relatively low temperatures are found during this phase. These fires are often burning for a long duration. Not much smoke transport, and there's not a strong smoke plume found during the smoldering phase. In the southeastern United States, duff plays a critical role in wildfires. Oftentimes, there's a deep duff layer that is common with some wetlands and wet temperature forests in the southeastern United States. Duff is normally burned during the smoldering phase of the fire. However, under extreme drought conditions, burning can occur during the flaming phase as well. And this was seen in the Rough Ridge fire in 2016. Emissions of duff burning is not well analyzed during the fire emission inventory at this time. So there's a gap in the literature, and we hope to understand how duff burning impacts air quality during fire. The overarching goal and objective of this research is to understand the contribution of duff burning to the air quality impacts during the 2016 Southern Appalachian wildfires. To achieve these objectives, we need to measure duff burning emissions. Once we get those measurements, we hope to simulate and evaluate smoke transport, compare fire emissions and air quality impacts between duff and above ground fuels, and compare PM 2.5 and ozone impacts of duff burning. I mentioned previously, we're going to be looking at the 2016 Southern Appalachian wildfire season. There are several large wildfires during this time. One of them was the destructive Chimney Tops 2 fire. In total, you had 91,000 acres burned during this wildfire season. For the modeling component of this research, the Weather Research and Forecasting Model with chemistry, or WRF-Chem, will be used. Version 3.9.1 was used in this study. WRF-Chem is a comprehensive regional atmospheric model. It's used to analyze atmospheric circulation, weather conditions, cloud processes, radiative effects, and atmospheric chemistry and aerosol transport. The model was run with a spatial resolution of 12 kilometers. Chemistry was updated every 3 minutes. There are different simulations that we ran during this modeling experiment. So we simulated with no fire. So that means no fire emissions with fire in the simulation. We also had a simulation using the FIN version 1.5. So the FIN fire inventory is applied with no duff burning. There's also a simulation with FIN and duff, where the FIN inventory was applied and we added duff burning treatment. Sensitivity experiments were also conducted where we doubled the FIN 2.5 emissions and we doubled the NOx emissions. And I want to point out a novelty of this study is including duff burning into the work chemistry model. This is something that we're undertaking. It's not a part of the model suite, and it's something that we're adding that's making this project novel. Duff emissions is just the duff mass that's burned times emission factor. Generally, there are 4.5 centimeters of duff burned each day during a fire. Duff burning emits more PM 2.5 per unit mass of fuel, but less NOx than the above ground fuel. The table on your right is a list of emission factors, the species, the emission factors for peat and duff, and for the FIN temperate mixed force. Here are some results from our model simulation. The following maps are showing PM 2.5 concentrations for no fire on your left, for the FIN simulation in the middle, and the FIN plus duff on the right. Simulations did a good job of capturing the PM 2.5 transport of fire and smoke. The FIN simulations underestimated surface 2.5 concentration by approximately 50% in areas with peak local concentration. This was slightly improved when duff burning was added. It improved the concentrations of PM 2.5 that were simulated. When comparing duff and above ground emissions, the PM 2.5 concentrations for duff burning are at the same magnitude or potentially slightly higher than those from emissions of above ground fuel burning. Implementing duff burning doubles the fire-induced PM 2.5 concentration over the study domain. Again, above ground is on your left, the duff simulation is on your right. Here's a look at significant surface PM 2.5 concentrations on the significant day of burnings during the 2016 wildfire. We have 3 locations that we're looking at: Macon County, North Carolina, Fulton County, Georgia, and Mecklenburg County, North Carolina. The simulated 2.5 concentrations increased by approximately 100% during the major burning days on November 7th, 8th, 13th, 14th, and 15th, due to including duff burning. simulations with duff improved the output of 2 PM 2.5 surface concentration in the Metro Atlanta region, Metro Charlotte region areas on major burning days. The above ground fuel burning increased surface 2.5 by 28.1% in Metro Atlanta, 41.2% in Metro Charlotte. Duff burning increased the surface PM 2.5 by 21.3% in Metro Atlanta and 29.7% in Metro Charlotte. Now to look at ozone concentrations on a significant burning day. Again, you have no fire on your left, the fan simulation without duff in the middle, and the fan simulation with duff on your right. The above ground fuel burning led to a 6 to 10 parts per billion increase in surface ozone on November 15, 2016 over the areas affected by the fire team. Adding duff to the simulation does not increase the surface ozone concentration. Looking at the comparison of duff and above ground emissions on significant days of burning. Over the downwind region, where ozone increases high from above ground fuel burning, duff burning is slightly offset by the ozone increase, up to 4 parts per billion. The ambient VOC concentrations are lower in November than in summer, which provides a VOC limited scenario in ozone photochemistry. In this scenario, when NOx concentrations are high due to the above ground fuel burning, more NOx emissions from duff burn tend to decrease ozone concentration. Looking at the ozone concentration profile for the same three areas of Macon County, North Carolina, Fulton County, Georgia, and Mecklenburg County, North Carolina, the above ground fuel burning increases ozone concentration by 15 parts per billion on November 13th to 15th. The ozone concentration and the fin simulation with duff are very similar to the simulations without duff, indicating that the duff burning has a negligible impact on the ozone concentration. The ozone simulation agrees more with observations in the urban areas than in the rural areas, as well as the fire area. The ozone in the urban area is not significantly affected by duff burning. Comparing the change rates for different simulations, we're looking at fire versus no fire, duff versus no duff, for PM 2.5 and ozone for different locations. We have fire region, which is the squared 6 by 6 area within the fire site in the center, Metro Atlanta and Metro Charlotte. Our results indicate that the changes are greater for PM 2.5, where you have a larger difference between the two. To test the robustness of our results, we did a sensitivity analysis where we doubled the fan PM 2.5 emissions. The doubling of the fan emissions did not affect our conclusion. There is still an underestimation of PM 2.5 when no duff was present in the model. The underestimation was 36%. Doubling the fan reduced the underestimation to 20%, but it was still a significant underestimation compared to adding duff in the model. We conducted a similar sensitivity analysis where the NOx emissions were doubled. Doubling the NOx emissions from duff does not change the result of the different PM 2.5 and ozone effects from duff burning. Increasing NOx further decreases the ozone concentration in nearby urban areas as well as the closest large major cities. In summary, the 2016 Appalachian fire event significantly impacted the regional air quality, including air pollution in urban areas. Duff burning had the largest impact on PM 2.5 emissions. That impact was comparable to the impact seen from above ground fuel burning. The impact on ozone production was not as strong. We proved that there is a need to include duff emissions in large reanalysis data sets, such as CAN and other global fire emission inventories to help improve the simulations of smoke impact. I'd like to acknowledge that this study was supported by an agreement between the United States Forest Service and the Oak Ridge Institute for Science and Education. Thank you.
Hi, everybody. Yeah, so Marcus and Yong is not here today. Yeah, he wanted to apologize for the sound quality on that. We think something maybe happened during the conversion, but I think it's a really interesting topic, and you know, a lot of these there isn't a whole lot of duff sometimes incorporated into these different models. That's pretty much all I can say about it. So Sama, how do you want to do this? Do you just want to hang tight for a few minutes, or if someone must have a discussion about it, they could?
Yeah, I think we should go ahead and just keep rolling into the next presentation, and we can give the next presentations an extra little minute or two for Q&A if we want to.
Okay, sounds good to me.
Yeah.
All right, so Zachary Robbins. Zach, you can go ahead and start sharing your screen. So Zachary Robbins is a PhD candidate at North Carolina State University. He's in the lab with Rob Scheller. So go ahead, Zachary.
Thank you. Let me get all the screens together. Can you hear me okay?
Yes.
Awesome. So I'm Zachary Robbins. I'm a PhD candidate at North Carolina State University, and I will be talking about some work I did today with Louise Loudermilk, Kate Jones, Matthew Riley, Joseph O'Brien, and Robert Scheller, looking at how to model future fire regimes in the Southern Appalachians. So we've all heard a lot about the Southern Appalachians today. I'm going to retread a little bit of territory there. So this is a highly diverse landscape with a unique geomorphology and a unique history of land use and land use change. It's a very crucial habitat for a lot of different species. Historically, it was maintained by fire very frequently through human ignitions and also through lightning, which kind of created open oak and pine stands across the landscape. The last 100 years of fire suppression and fire exclusion have led to increased densification within the area and also an increased mesic hardwood component through the process of mesification. This mesification has the ability to kind of reinforce the fire regime by altering the ability for fires to occur, by altering the fuels and the understory component throughout the region. And this is particularly concerning because species like oak and pine are unique habitats for vegetation and also for wildlife on this landscape. So the reason this session was kind of convened was this 2016 fire season that occurred. On this chart, I have the hectares burned per month going back to 2000. And then in the red, we have the monthly mean fire weather index there. And as you can see in October and November, that fire weather index really spikes up in 2016, and that leads to this large amount of fires across the Southern Appalachian landscape. As many people have talked about here, this is a landscape that readily has fuels on it that, due to the high productivity, return relatively quickly, but really often requires these late fall drought conditions and overwinter kind of dry conditions in order for fires to burn on this landscape. So obviously in kind of seeing this anomalous fire weather index event, we're kind of concerned as to whether could this become more predominant in the future? And so kind of looking to connect drought and fire and that prevalence in the future, if we look at climate models within the Southern Appalachians, they project increasing temperatures, 1 to 1.5 degrees by the middle of the century and 3 to 4 degrees by the end of the century. Climate models often predict increasing precipitation for the region. However, this could be offset by rising evapotranspiration from that temperature, which may still increase the amount of drought in this area. However, climate projections for the southeastern United States are notoriously bad at capturing precipitation regimes, primarily owing to the fact and their difficulty capturing sea surface temperatures and how that affects the overall precipitation regime. And so our study was kind of looking at, well, given that uncertainty, can we understand the bounds of what drought will look like in the future and what fire might look like in the future? So to do this, we had to do a couple things. The first was kind of understanding what the climate models themselves say with regard to future drought patterns to select out different climate models. And the next was capturing the fire, weather, and fire relationship for this landscape. We did this using data on fires and fire burned area, as well as spatially explicit climate models, models of topography on the landscape. We then fed this into a Landis-2 model that simulates the vegetation and the soils so that we can capture those dynamics of the fire regime in order to test a couple different hypotheses. The first hypothesis was that this an increasing drought trend would increase the total area burned on the landscape. The next is that increasing drought variability would increase the total area burned. This is based off, we saw in 2016, it only takes one kind of droughty year to really account for a lot of the fire on the landscape. So you could imagine, even if the trend was consistent through time, increased variability would provide for more of those years. And our third hypothesis was that even reductions in the fire return interval would likely not be sufficient within the simulation to revert species back to historical conditions. As I said somewhat earlier, currently the fire return interval for this landscape is so much longer than it was historically. It would really take a radical shift in the fire regime to restore those conditions. And furthermore, many of these mesic species have firmly established within this area. And so our hypothesis was that these reduced fire return intervals would not be sufficient. So here we are looking at the climate scenarios that are for the Southern Appalachians. On the y-axis, you can see the ratio of precipitation to potential evapotranspiration, which we used as an annual measure of drought through time. You can see as that number gets lower, that would be an increased drought year on the landscape. We selected models that represent a major drought trend through time. Those are the two models on the left, while the two models on the right represent a minor drought trend through time. The two models on the top represent low variability through time, while the two on the bottom represent high variability through time. We also had to capture these dynamics of how fire weather interacts with fire on the landscape. To do this, we used a scrapple model within Landis-2. This accounts for accidental ignitions as well as lightning ignitions on the landscape as a function of the fire weather index, and it spatially distributes them based on lightning climatology and also the history of where accidental ignitions most likely occurred. It also has a model to simulate management and prescribed fire on the landscape. It calculates spread as a function of the fire weather index, the fine fuels that are present, and the effective wind speed and topography on the landscape. And it additionally includes site level and cohort level mortality models that we parameterized based on field data from 5 fires across the landscape. So here's kind of some of the things we saw in parameterization. For ignitions, we fit a zero inflated Poisson model that shows that as fire weather index increases, the probability of zero ignition days as far as lightning concerned decreases, but also the probable count of ignition decreases. This might capture the rare conditions in which lightning can occur on this landscape that have to both be dry enough that an ignition would occur and wet enough that there would be lightning in the air. For the accidental ignitions model, the model seems to be much simpler. As fire weather index increases, the probability of ignitions increases through time. There would be more more ignitions on the landscape. Some of the things we see in our fire spread model that we parameterized for the landscape is that fire weather seems to be the dominant determinant of how likely fire spread is on the landscape, with fine fuels being the second most common determinant. You can see as we get to a fire weather index of 20 to 30, you really get to a net positive probability of spread, but that fuel can kind of determine as where spread is happening on the landscape. So you have kind of fire weather as the ultimate determinant of fire spread, with those fine fuels kind of determining where it's most likely to actively spread on the landscape. We also parameterized a model of fire suppression. We created a fire suppression rating system based on where fires would be most easily suppressed. That was based off of topography, as well as road access, whether the location is within the WUI or whether it has a wilderness designation. All of these hopefully trying to capture some amount of how easy is it to access a fire, and then how ardently would a fire be suppressed within those areas. We then took those different ratings and parameterized them based off historical data of fire in the area in relation to our fire spread model. This is particularly useful because we can then, in future studies, manipulate some of these characteristics to see how they will change over time as, say, suppression increases or as the wildland-urban interface expands. In validating our model against the historical record, we found we captured quite well the total hectares burned over the study period, as well as the fire size distribution and the distribution of severity across the landscape. In looking at the interannual variability and how well we capture that, we find that we capture about 46% of the variability in the annual number of fires. Now, this is a stochastic model, so there's a lot of kind of variance, particularly in those high fire years. And what we determined from this is that fire weather seems to be the dominant condition that kind of lays the groundwork for large fire years, but it really depends on ignitions in somewhat more isolated areas where suppression is hard occurring during that time period to get these big fire weather years. When we look at the results of our climate modeling for those 4 different scenarios, I'll start with the purple here. This is a historic representation, so we just randomly sampled historical years for an 80-year time period. You can see under our climate scenario with low drought increase and low variability, that's very much akin to the historic period. So we don't see a big change in the number of hectares burned. However, if we increase the drought variability through time, we find that the total hectares burned increases by about 50%. If we increase the drought trend over time, we find that it increases by about 150%. And the combination of increased drought and increased variability increased the number of hectares burned on the landscape by about 500%. This is a really radical shift in the amount of fire that would be on the landscape and speaks to kind of that threshold we talked about before where there are adequate fuels, but in this incredibly dry and variable condition, the amount of hectares burned increases greatly. We also looked at how these were spatially distributed across the landscape. As you can see across all the different climate models, there are areas where fire is concentrated and where it is more sparse. This speaks to the level of suppression in different areas on the landscape. In that most extreme scenario in the bottom right, we can see a sort of radical shift in the fire regime from many hundreds of years in the fire return interval down to as little as every 25 years fire occurring. We find that larger fires are most likely to occur in national forests where there are relatively few roads and where suppression would be more difficult. Another aspect that is somewhat concerning is as the total amount of fire on the landscape increases, the area impacted by fire increases as well. So you can see in that upper left scenario, only about 20% of the landscape would be expected to be impacted by fire over a 200-year period, while in the bottom right scenario, about 80% of the landscape would be impacted over a 200-year period. This is particularly concerning for this area, which has a very large wildland-urban interface that is expected to expand over the next century. Oops. Sorry about that. We also looked at how the fire return interval affected species composition across the course of an 80-year simulation. Here I've binned all the climate runs together to just look at individual sites based on fire return interval. The initial landscape state is there in gray, and then the subsequent fire return intervals follow after that. What we can see is that in these most extreme fire return intervals, or the shortest fire return intervals, it does increase the amount of oak on the landscape while decreasing the amount of maple. However, it is unable to move the amount of mesic hardwood on the landscape. So this suggests that these species are somewhat able to establish, they're able to re-sprout within the model following these mostly low severity fires of the future, and are able to persist on the landscape even under a smaller fire return interval. So some of the takeaways from this presentation: overall, the climate models predict a wide range of future fire regimes, and these seem to be primarily driven by the frequency of drought in the future and the variability of drought within the future. There are strong spatial disparities in the fire return interval under all climate scenarios that seem to persist and will be important to consider when using fire as a restoration tool on the landscape. We also see that fire suppression will play a crucial role in the ecology of this landscape, even under climate change. So fire suppression and climate change both are going to shift the fire regime on this landscape, and that's an important consideration. And lastly, mesification in many of these areas seems firmly entrenched, even under radically lower fire return intervals. Some future research that we hope to do, as I said, from this study, we kind of saw that fire weather index seems to be driving some of these fire size, at least within our simulation, but that requires ignitions in sort of remoter areas where fire can spread. Additionally, we saw that fine fuels contributed to the fire size. So our next goal is kind of identifying the relative importance of different management strategies and how those contribute to fire overall, looking at things like reducing human accidental ignitions, increasing prescribed burning on the landscape, looking at suppression changes, particularly in more isolated areas, and then looking at the future of land use change in this area. Also using this modeling framework, Kate Jones, who will be talking at 4:20 Eastern, will be looking at prescribed fire, smoke, and communities, and how those will all interact under climate change. With that, I will take any questions that you have. I'd love to thank my collaborators, as well as our funders at North Carolina State University, the ORISE program, and the Forest Service, and Karen Short for creating and maintaining the spatial wildfire occurrence database.
Thanks, Zachary. Okay. What kind of questions y'all have? I don't see any, and you guys are so quiet today. It's amazing.
Louise, I've got a question.
Absolutely.
So, hey, Zach, thanks. So I was just curious, when you're showing the maps of a future fire, future area burned or fire, I can't remember what it was, fire frequency, across the whole landscape, it really looked like the southwest borders of your landscape were showing the greatest increase and the most burning. And so I'm just wondering if you have thoughts on why there.
Yeah, well, I guess primarily, you know, a lot of those areas are sort of in that national forest band where there's kind of less access for suppression based on the road frequency and kind of where the wildland urban interface is set up. And so I think the model is kind of capturing that dynamic. I think also because it's at the southernmost area of the study area, that's kind of where we see the fire frequency, or sorry, the fire weather index increasing the most rapidly.
Hey, Louise, I have a question.
Absolutely.
Zach, I was interested to know if there were any attributes of forests that would make them good candidates for restoration through fire for those xeric oak species. I'm thinking of like a percent of mesic hardwood makeup or something like that.
Yeah, I don't have that result necessarily right now, but that's really a thing we'd kind of like to look at in the future, is using some of these simulations to kind of identify landscape characteristics as well as stand characteristics as to, you know, where it seems like returning fire might be able to, under different climate scenarios, be the most adaptive, and where it seems like, you know, perhaps mesic species are already so established, or the landscape position is such that it just seems unlikely that those will really establish. But as to that analysis, I kind of only looked at the landscape as a whole in these simulations.
Hey, Zachary, I sort of had that a similar question. I was curious. It's that rising tide of mesification at the regional scale. There's just no way to sort of turn that back, but it seems like maybe you do have the potential to zoom into specific landscapes or and make that same figure for smaller scales in places where fire frequency projected in the future might differ.
Yeah, I mean, I think that could be a really cool thing to look at, is just within individual scales, where was the shift the largest versus where was it just maintaining? You know, in that figure, we have kind of this flat mesic hardwoods that even when they're hit with fire somewhat repeatedly, seem to still make up a significant portion of the biomass over time. A similar figure kind of combining this and the previous figure might be nice to see what areas seem to be the most able to revert.
Yeah, good stuff, thanks.
Yeah, thank you.
Okay, well, if there's no more questions, I think we can keep going. Okay, that's going 3 times. Thanks, Zachary. Yeah, let's transition to Melanie. Melanie, you can go ahead and start sharing your screen.
Okay.
Zach, yeah, there you go. Okay. Melanie Taylor is a soil scientist with the USDA Forest Service in the Southern Research Station. And Melanie, take it away.
Okay, thanks, Louise. It's my pleasure to be here talking to you today, and I'm going to be talking to you about some research from our group on the Southern Appalachians, some of which was published earlier this year in a paper led by Dana Carpenter, which included Louise and myself and others. And then I'm going to talk to you about some newer findings that are hot off the press, so to speak, that are from the same sites. So I am here, of course, to talk about the fires that happen in the Southern Appalachians, and specifically one that happened close to us here in Georgia. And the one we used as the basis for our study was the Rock Mountain wildfire. So this fire occurred after a warm and dry fall in the Southern Appalachians, which you've heard other speakers talk about. And it started in northern Georgia and spread north into North Carolina. And here's a photo of the fire that was taken during the fire that captures what most of it was like. And that was with these short flame lengths generally, and this persistent smoldering of the organic horizon. And I'm going to talk a little bit more about that later. So this fire was the motivating factor of the study that we subsequently set up. But as you know, and as others have spoken to, there are many contributing factors to the current state of forests in the eastern US, including those in Southern Appalachia. And those things really influenced the questions that we posed and how we designed our study. So I'm going to give a bit of background on those contributing factors just briefly, and then I'll get into the methods and results. So over the last century, tree species composition of Eastern North American forests, including those in the Southern Appalachians, has changed from primarily oak and hickory species to forests that are increasingly dominated by tulip poplar and maple species. And I'm kind of glossing over several events that happened in that transition, but for the sake of time, this has been the overall direction of change. So we think this is occurring due to a couple of reasons. The one that has already been spoken about is fire exclusion, and that's because, as others have noted, until around 1 century ago, eastern forests burned regularly, which selected for fire-adapted species like oaks. And fire exclusion in these forests has led to the encroachment of fire-intolerant species, and that includes tulip poplar and maples. Another mechanism of this change is altered nitrogen cycling, and that's happened because nitrogen has been deposited through atmospheric deposition, and that's created these high nitrogen soil environments that select against tree species that have nutrient conservative traits, and that includes oaks and hickories. So accompanying this tree species change that I've described, there's also been a shift in the dominant mycorrhizal association type from primarily ectomycorrhizal or ECM, which is the type of association used by oaks and hickories, to increasingly arbuscular mycorrhizal or AM, which is the type of association used by tulip poplar and maples. Now, just to back up for a second, if anyone's unfamiliar with what mycorrhizae are, I expect that most of you probably know, but just in case, there are these associations between roots and soil fungi, where the trees trade carbohydrates for nutrients from the soil. And the reason why we care about the change from one type to another is that each type has been shown to have its own so-called biogeochemical signature. And that's because ECM-dominated forests have been shown to have forest floors that have a higher carbon to nitrogen ratio. And also they've been found to have a suppressive effect on rates of decay, which potentially has further far-reaching effects on ecosystem processes. When we were developing our questions about how the Rock Mountain wildfire would impact forests, we wanted to ask how the return of fire would impact forests undergoing this transition from oak hickory ECM to maple tulip poplar AM. And this is important for a couple of reasons. The obvious one is to understand the impact of the wildfire, but also secondary to that, there's a management interest in using fire to halt and or reverse this transition. But the effects of fire on forests that have had fire excluded for a century or longer, those are poorly understood. So encapsulated within that big question, we also wanted to know if AM or ECM trees were more susceptible to decline post-fire. And we asked, what are the effects of fire on these established mycorrhizal biogeochemical patterns that we know are likely to exist? So we knew that in order to answer our questions, we would need to identify forested stands that represented a gradient of this transition from ECM to AM. And we would need to find those in both burned and unburned areas. So in this gradient that we wanted to set up, 100% ECM basal area represents an area that is all ECM trees, so all oaks, hickories, pines. And 30% means 30% of the basal area is made up of ECM trees and 70% is made up of AM trees. So this is a photo of a soil monolith, which is just a cube of soil that was dug out of the ground. And this one is from an unburned area near the Rock Mountain fire. So this one stayed mostly intact and cube shaped as it was removed from the ground. And I think that's what prompted me to grab my camera and take a photo. But you can see that deep OEA horizon or duff layer that has formed on the soil surface. And you've got the human arm there for scale. So you can see that it's quite thick. And if you look closely, you can see that this layer contains lots of roots. So knowing that ECM dominated forests tend to suppress rates of decay, we hypothesized that this organic horizon would be deeper and contain more roots in higher percent ECM stands. And following that, we hypothesized that those deep organic horizons were more likely to be consumed by the fire, and that therefore we would find that trees in higher percent ECM stands that had burned would experience more decline. So in order to answer those questions, we established 32 plots across our mycorrhizal gradient and across the fire perimeter. Plots were distributed across 4 spatial blocks and 4 topographic positions as well. So in those plots, we measured organic horizon depth and mass. We measured fine root biomass, and we measured tree stress and mortality. So here we're looking at the OEA or duff horizon depth on the y-axis and the percent ECM basal area on the x-axis. Burned plots are in red and unburned are in blue. So we found that the OEA horizon was deeper and heavier in unburned plots, and that it was positively correlated with percent ECM basal area. So this tells us that that duff layer, that OEA horizon, is building up more so in higher percent ECM stands, where we can see it was consumed during the fire. Here we're looking at fine root biomass, and the colors are the different soil horizons. So we found that fine root biomass and length in the organic horizon increased with increasing percent ECM basal area. And this was higher in unburned plots. And you see that this is not true with the 2 deeper mineral soil layers. So this tells us that in the figure from before, that higher percent ECM basal areas are building up those deeper organic horizons. And this tells us that when that horizon exists, those trees in higher percent ECM stands are more likely to put their roots into them, where they get consumed during a fire. And here we're looking at the probability of trees being in different crown classes 3 years after the fire, which are shown here in different colors. And burned plots are on the left, unburned are on the right. This yellow color is 76% or greater crown remaining. So you can think of that as the healthiest class of trees. You can see that the probability of that class decreases sharply with increasing percent ECM basal area in burned plots, but not unburned plots. So these results from Dana's work led us to ask, why does this OEA horizon build up in higher percent ECM stands? Well, we hypothesized that this buildup was due to that suppressed rate of litter decay in ECM-dominated stands. Remember, I told you earlier that they've been found to suppress decay. Well, we hypothesized that we would observe that pattern along our mycorrhizal gradient, and that percent ECM basal area would be correlated with different community compositions of soil and litter macroinvertebrates that are also important in the decomposition process. So further, we expected that the reintroduction of fire after long-term exclusion like this would slow decay further through its negative effects on those macroinvertebrate communities. Oops, sorry. So to answer that question, we measured litter mass loss over 3 years in a subset of the plots from before. So we put out litter bags, which are shown here in this photo, with either AM or ECM litter, and we calculated the litter mean residence time, which is just the average time that litter remains. To answer our macroinvertebrate questions, we hand collected macroinvertebrates during 3 seasons from soil monoliths, like the one that I showed you before. So we dug those monoliths out and put them on a tarp like this, and then they were hand sorted for invertebrates twice, and that's what these people in this photo are doing. We also searched a 2-meter radius subplot for litter macroinvertebrates. And so we got all those organisms, preserved them in ethanol, and brought them back to the lab. And we sorted them into broad groups like beetles, spiders, worms, etc. And we're still kind of working up this data, but so far we've analyzed the community composition, and we've looked at those with NMDS and Permanova. And similar to before, we're looking for effects of our mycorrhizal gradient and burn status, along with season and block, which we thought could also be important. So first, let's take a look at litter mean residence time. On the plot on the left here, burn plots are on top and unburned are on the bottom. The x-axis is our mycorrhizal gradient. So we found an interactive effect of burn status with percent ECM basal area, with unburned plots showing an increase of mean residence time with increasing percent ECM basal area, and burn plots showing the opposite pattern. So as you can see on the box plot on the right, litter type was also an important main effect in this model, with ECM litter having a longer mean residence time than AM litter. And these results give us some insight into how litter decays in these forests and why that OEA horizon builds up in higher percent ECM stands. We can see that the context of decay is important. So in the unburned plots, not only is ECM litter decaying more slowly everywhere, but litter decays more slowly in higher percent ECM stands. So these two effects combined lead to higher percent ECM stands having deeper organic horizons. So in the burn plots on the top of that figure on the left, there's more variation across the ECM basal area gradient. But interestingly, the pattern and the pattern's a bit weaker and the slope is in the opposite direction. So this is contrary to our hypothesis, and it means that litter's decaying more quickly in higher percent ECM stands that were burned. So I'm really interested in understanding how changes due to fire lead to these heightened rates of decay. So now looking at community composition of broad groups of macroinvertebrates. So I'm going to present the analysis from litter and soil separately. And this is an NMDS plot. Each point here is one sample and points are colored by percent ECM basal area. And the shapes are either burned or unburned. So after accounting for season, which was important in our model, and for block, we found an effect of percent ECM basal area and burn status, but not their interaction. So that suggests that separately, percent ECM and burned or unburned are important for community composition in those broad groups. And a similar situation with the soil macroinvertebrates. After accounting for season and block, percent ECM and burn status were both important, though interestingly, percent ECM effect size is higher with the soil macroinvertebrates, which I'm really interested in getting into that a little bit more. So just to give, I just started looking at the abundance data for the macroinvertebrates. So this is just like a little teaser, but just to give you an idea for what we saw. So we collected nearly 2,000 organisms, and those are sorted into 23 different groups. So what I'm showing you here is only the 10 most abundant groups, which contained over 97% of the total number of organisms. But by far the most abundant organisms we encountered were millipedes, followed by immature beetles or grubs, and then by worms, spiders, centipedes, and adult beetles. So I'm really excited to dive into this data more after looking at the community composition data to work out what groups are driving that community composition difference that we saw. So putting all these results together, in conclusion, we found that in the absence of fire, higher percent ECM forests accumulate organic matter, where we found that trees put their roots that are then at risk of being damaged or consumed when a fire occurs. The loss of those roots to fire has a delayed negative effect on trees that are generally considered to be fire adapted. So that, I think, is a bit of a cautionary tale that the reintroduction of fire can have delayed negative effects on trees, and that occurs due to the novel fuel situation caused by long-term fire exclusion. So we found that organic horizons build up higher percent ECM basal area, organic horizons build up in higher percent ECM basal area stands, and that's due to the effect of litter quality and the mycorrhizal basal area context of trees in which that litter is being decomposed. So our community composition data on soil and litter macroinvertebrates also suggests that these organisms could be part of this mycorrhizal effect on decay that is interesting because that has generally been considered to be solely a microbial phenomenon. And it's interesting to think about how fire influences those community compositions as well. The next steps for this project that I already alluded to a little bit are to further analyze those macroinvertebrate abundance data to better understand the effects of fire and the percent ECM basal area on these different fauna groups. So every part of this, from the design to the field work and the lab work, Dana's paper, revisions, new ideas. So this has all been a massive undertaking and really couldn't have happened without the work of all of my co-authors and each of these individuals. With that, I'm happy to take any questions now or by email, and here is my email address. Thank you for your attention.
Whoops. Thank you, Melanie. That was awesome. Okay, any questions? I don't think. Let's see, anybody?
Hey, Louise, I don't have a question, but just the last couple talks and the musification, and I'm just really learning a lot about that process. And I think Adam's talk and Melanie's talk and Zachary's talk all have some really interesting sort of similarities there looking at that. So I'm learning a lot. I appreciate it.
Yeah, absolutely. And yeah, we've talked a lot about some of these different new concepts in terms of modeling, right? In some of Zach's work. So yeah, Melanie, do you think, I mean, what does this mean, for management in the long run?
Yeah, I think it means that we, which fire managers probably already know, but as someone who's more interested in soils, this is something that I'm learning, that we really need to be careful when developing prescriptions for landscapes, because it's easy to just think, well, just burn it and it'll go back. But I think this study and the other studies that I've seen in this session really suggest that, that's probably not the case, and that it's going to require some other management technique in order to manage fuels, and something that has to be thought about, I think.
Thanks, Melanie. Sama, other questions on HUVA? I don't see any on mine.
Nope, no questions on HUVA.
Louise, I see a couple questions.
Okay. Would you mind fielding them?
Sure. The first question is, did you measure abundance of the fungi themselves? From Rob Klein.
No, we did not. We just knew the percentage of ECM versus AM basal area.
Gotcha. Next question from Rob Klein. I'm curious how fungal biomass itself may have changed after the fire.
Yeah, that's interesting to think about. I'm sure the fire had a negative effect on all fungal biomass that is pretty heavily concentrated in that surface most organic horizon. ECM forests tend to be more fungally dominated. So it is interesting to think about if the fire is burning the duff layer, which exists in those higher percent ECM stands, how that sort of feeds down into fungal biomass.
Thanks for fielding those, Robert. I got one more for you from Matt Vaughn. I really like to look at ECM versus AM associations. What was the inspiration to categorize this way for the analysis?
Yeah, it's really interesting, and I don't want to dive too far into my life story with that, but I kind of feel the desire to. So I come from a background where I'm more interested in sort of biogeochemistry and root processes. So I had experience with AM and ECM differences when I got this job with the Forest Service. And so being here with the Center for Forest Disturbance Science and learning more about fire and how fire impacts these things, it was really just kind of like the perfect storm, so to speak, for me, using that angle to look at this idea of fire effects.
Okay, thank you. Were there any other questions in there?
That is it. Thank you for your time, Melanie.
Thank you.
Okay, last but definitely not least is Kate Jones. You can go ahead and start sharing your screen. Kate is a graduate student at North Carolina State University. And Kate, I'll let you take it away.
Thanks, Louise. Can y'all hear me all right?
Yes, I can.
All right. Hi, everyone. As Louise said, my name is Kate Jones, and today I'll be talking about a chapter of my dissertation that's not quite underway, but it's getting there. And actually in the next couple of weeks, we'll be having our first meeting for this project. But it is forecasting prescribed fire smoke in Southern Appalachian communities. And so I first want to thank my co-authors on the left of the slide here, as well as our research and management partners, which are the Consortium of Appalachian Fire Managers and Scientists, the Nature Conservancy, the North Carolina Wildlife Resources Commission, and the U.S. Forest Service. And this work is funded by the Joint Fire Sciences Program Grant Award, as well as the Center of Geospatial Analytics. So this work, or kind of the brainchild for this work, is at the confluence of kind of 4 different topics, interrelated, but I have them separated out here. So as I was having conversations with different fire managers in the Southern Apps, these were kind of the most relevant topics or common ideas that kept coming up. And so in the top left, we have increasing fire use. So not necessarily increasing wildfire frequency or severity, which I know a lot of these talks are predicated on the 2016 fires, but really thinking about increasing prescribed fire use, perhaps into response to more severe wildfires, more frequent wildfires, increasing crew capacity, number of acres burned, and overall frequency of burns. But that is happening alongside this process of infilling and expanding wildland-urban interface, or WUI, in North Carolina. And so the map here from the Silvis Lab shows the wildland-urban interface in orange and yellow here for the state of North Carolina. And North Carolina ranks first in total number of acres in the United States in the wildland-urban interface, and 4th for both housing units as well as population in the WUI. Now, these data are from 2010, so a bit dated at this point, but the update for 2020 is forthcoming. And we see both an expansion of WUI and infilling, so a densification, and even if it's not occurring at the same rate as maybe managers or other people have noticed in the past, we still have this high percentage of WUI on our landscapes in Western North Carolina. And so the bottom left, this kind of third idea or topic that contributes to this work, was born out of a conversation with actually Margaret Bucher at the Nature Conservancy a couple of years ago now. And she posed the question of who are our neighbors? Who are interacting and existing within our fire management decisions on these landscapes? And so the map in the bottom left shows the Appalachian Resource Conservation and Development Coalition counties. So places where fire adapted community programs are already in place, or fire awareness programs are in place. But this doesn't really give us too fine grain or too high a resolution look at who are those people? Where are they at a resolution finer than the county? And what are their characteristics? What might existing community vulnerabilities that would maybe change how we communicate, how we plan, or how we think about a more community aware management strategies? And so the last kind of idea weaving into this is we have uncertainty with how climate in the Southern Appalachians will change. Zachary discussed that a bit in his talk, which we'll continue with some framing later on. But so there's climate uncertainty, there's management uncertainty about what prescriptions are we going to put on the landscape, which I really liked how Melanie kind of raised some questions about what is the best way to get to that end result in fuels reduction and restoration. So how do climate and management interface to effectively change or influence smoke production into the future? So we're taking this long-term look at cumulative smoke production. And in doing that, we're hoping to do our best to bound some of that climate uncertainty, so represent in members of climate expectations using different climate projections, as well as adjusting fire management considerations, different aspects of a burn prescription for any given unit on the landscape. And so our motivating questions here are, how do burn intervals, forest succession, climate, site location influence where and how much smoke is delivered to downwind communities? So we're really trying to weave in the increasing prescribed fire, extending development, who are the neighboring communities, and how do climate and management all work together in this space? And then the second question is, which prescribed fire sites are more likely to experience future burn restrictions due to WUI development? And maybe burn restriction isn't the exact proper way to phrase this, but where do we expect to see prescribed fire smoke dispersal interacting with communities on our landscape now, as well as into the future? And we'll talk a little bit about that WUI into the future element. So the way this project is designed or kind of falling out, we are first starting with co-development. So those management and research partners that I mentioned on the first slide, to really work together, draw on maps, kind of sketch things out. Which sites, which fire management units are we interested in modeling some of these, future prescriptions, future management programs? And so to do that, we're really starting off with the goal in mind of producing management relevant research that addresses mid to long-term prescribed fire smoke production. And the map on the right is, like I said, this work is just getting underway. We haven't even had our first meeting yet, but really a hypothetical infographic, if you will, of what we might expect or how we could describe what our sites and scenarios might be once this project is underway. So we're on the Tennessee-North Carolina border, and some of you will recognize that black outline from what Zachary showed in his presentation. So the gray outline is our modeled area. So where we have a parameterized landscape forest change model. And so these hypothetical sites here are A, B, C, and then the bar charts associated with them represent the idea that we have different land change or management scenarios that we hope to run for each site. And so to describe what a scenario is, you can look at the table just beneath the map. And for site A, we have, again, hypothetical scenarios of frequent burn, restoration, fuels reduction, first burn. And within each of those scenarios, we can start to toggle and play with some of the management decisions or management priorities that might occur for any given site. So adjusting the burn interval, the burned window, whether that's now or into the future, shortening, lengthening it, different weather constraints, as well as those different climate projections. Again, trying to bound that hotter, drier environment, hotter, wetter. How does climate all factor into this? And so our co-production process is effectively a combination of trying to solicit information ahead of time. So we started with a pre-meeting survey that is shown here. The first map, I guess, we delivered to the managers was write down, jot your thoughts. What are the sites that you are interested in seeing this kind of smoke forecasting work done for? Or where do you have existing smoke concerns right now? And so our modeled area, again, is in white, and then just some different management overlays or ownership overlays for reference. We also included 15 different, short or multiple choice or free response questions. Examples are, 10 and 12 beneath the map, trying to really get at different nuances that might be relevant for this type of community aware, long-term prescribed fire smoke scenarios. And so my job is to synthesize the responses from that pre-meeting survey before we have that meeting in the next couple of weeks. And the reason we used a pre-meeting survey is particularly over Zoom, but also in any large group meeting, it can be difficult to communicate the detail of what you're thinking, the nuance of a certain scenario that you might be interested in. And so we wanted to get all of that in writing, give everyone a chance to really document their thoughts and their expertise that they're bringing to the table, and then have a discussion about that once we're in our first meeting. So hopefully we'll have some sites determined, as well as the beginning, the foundation for some of those scenarios for each site in our next meeting in a couple of weeks. And then the flow chart here kind of represents how we'd like to move through this co-production process throughout this project over the next couple of years, all the way down to what is the most relevant delivery of these data products to different practitioners and managers. So after some of the deep thinking about where and what to model, it will be my job to actually start those model simulations and get them underway. And here, these are the two models that we will be using. So you heard a little bit about Landis 2 from Zachary Robbins' presentation earlier, and I am benefiting tremendously from the work that he has put into parameterizing the model for this area and really the entire dynamic ecosystems and landscape lab at NC State. So Landis 2 is a cell-by-cell forest change or forest succession model. And the neat thing about Landis is it's spatially interactive. So each cell, this black squares here in this figure on the left, is aware of what's going on in its neighboring cell, which is pretty important when you're trying to simulate fire spatially. And so for each Landis scenario, again, at that table at the bottom, we can initiate different amounts of fire, different fire sizes, different frequencies, and all the prescribed fire simulated in Landis burn within a single day. There's weather parameters associated with them, winds, etc. So for every fire that burns, we will then trigger a V-smoke smoke dispersion simulation. So under V-smoke, you can see a landscape image of 3 different V-smoke plumes that are just example runs that I did. And V-smoke is capable of simulating a smoke plume up to 60 miles from the source, which I think is a pretty critical thing to kind of focus in on. We're looking at very localized smoke dispersion and cumulative smoke footprints when we're thinking about communities here. And V-smoke is a Gaussian dispersal model. So a little infographic on the right, imagine a cone coming away from an ignition source. And then you can see the green distribution at the left, the blue distribution at the bottom. Those represent, the vertical portion of the plume, the horizontal version of, or direction of the plume. And the red dots are where you would see the highest concentration of PM 2.5 is specifically what we're interested in. And so that would occur, at the center of the plume. So V-smoke is also deterministic. So every parameter that we get from Landis, we run V-smoke with that, we'll get the same answer each time, which sometimes is a limitation, but for our uses, we plan to kind of stochastically perturb some of the more estimated parameters for V-smoke. So when we trigger a fire in Landis, run a smoke dispersion model, we're going to run a series of Monte Carlo simulations as opposed to just one V-smoke footprint that will be returned. And the benefit of using V-smoke, which I will talk about the limitations on the next slide, is that it doesn't require 3D gridded meteorology. So we're trying to forecast smoke dispersion, cumulative smoke footprints, 20, 30, 40 years into the future with a long-term change model. We don't have forecasted meteorology in these scenarios, and we also don't want to increase the uncertainty in the meteorological assumptions that we're making. So maybe validating isn't the perfect word, but for V-smoke, we know it has limitations. It's still our tool of choice because of that simplified meteorology. And so this map on the right represents gold markers and brown markers represent EPA air data quality monitors. And so we plan to really just create a baseline of V-smoke simulations so we can start to understand bias in V-smoke. Does it change seasonally? Does it change with different weather patterns? And to do that, we'd like to go back to kind of recent historical records, so maybe 5 to 10 years, find prescribed fire sites that are in close proximity to these air quality monitors, run V-smoke simulations, again, with some stochasticity, and then check the EPA data quality monitors and what the values they recorded. And so we don't expect these to align perfectly in any way, shape, or form, but it gives us a starting point, a conversation for how our model runs might be biased as we look out to the future. And so the third component, getting back to that idea of communities, who are our neighbors, and why might that matter for mid to long-term landscape planning. So the community data is kind of broken up into two sections, if you will, the WUI as well as the social vulnerability. And so starting with the WUI data, this map shows the wild and urban interface in Western North Carolina from 1990, 2000, and then a final time step in 2010. And again, we hope that the 2020 data will be available as soon as census and all those other data products that go into it are processed. However, we can still start to pick out some patterns here. So the most vibrant oranges and yellows are the most recent. And the orange, so the intermix of the WUI, tends to occur around the periphery of already existing WUI, so 2000 and 1990. Whereas the vibrant yellows tend to kind of occur at the core or start to infill in already WUI designated places. And so we're not interested in any of this forecasting in predicting. We really want to project with likelihoods and comparative scenarios. And so to do that for the wild and urban interface, I'm hoping to build off some work of another PhD student, Alexander Yoshizumi at NC State, who is working on quantifying development drivers in Western North Carolina. So not saying this place will or won't develop, but rather this place has the characteristics of sites or areas that have developed in the past. And these drivers are consistent or inconsistent in both space and time. So hopefully we would end up with some type of indicative WUI map where we can really start to overlay that with prescribed fire sites that are selected for this study and see where those phenomena start to intersect. And then finally, we have what existing community vulnerabilities might we want to know about or need to know about that we haven't evaluated in the past, particularly in a smoke management context. So mapped here is the social vulnerability index, which purple represents high vulnerability, white is low. And this index is actually made up of 4 different components. So socioeconomic, household composition, minority status, whether or not an individual is a native English speaker, and then housing type and transportation. So whether or not a home is owned or rented, whether or not it's in a group housing scenario, access to public transportation, an own personal vehicle. All of those metrics are captured using census data. And so this is represented at the resolution of a census block. And so if you start to map these 4 metrics, so socioeconomic, household, et cetera, those metrics themselves on a map, so this is the composite that you're seeing, the patterns start to change in space, which may or may not have implications for how we think about management. But if we can start to get a more fine resolution map of community characteristics and data, and again, overlay that with management sites and cumulative smoke delivery from those sites, what might we learn from those conversations and just having that spatial data mapped in front of us? So to bring this all together, the take-home point is really, we're trying to explore future fire use, so specifically prescribed fire, with an emphasis on neighboring communities. And so the map here on the right is an example of a number of the final data products that we will have for any given simulation for site. So you can see the social vulnerability, the wild and urban interface, as well as the V-smoke different footprints. And so this is for, again, hypothetical site A, say an oak restoration scenario in the first decade. So this is a small fraction of the total data that we might have as a final output. And we're still working through, I think, the best way to summarize these data products, to provide them maybe in some type of interactive interface where practitioners could toggle off and on data layers, different scenarios, different sites, and even the best way to summarize some of the actual data products. So in this case, the V-smoke footprints, showing a deterministic oval is not, it's not accurate nor predictive, a usefully predictive thing. So we might like to see some cumulative kind of like hotspot or heat map of smoke throughout time across scenarios. So with that, if anybody has suggestions about good visual tools or ways to go about communicating this data, I will take any questions.
Thank you, Kate. All right. If anybody can see any questions, or if anybody would like to voice a question to Kate.
Hi, can you hear me?
Yes.
I can.
Hi, I put a chat or a question in the Q&A chat box, but I can just go ahead and read it. So Kate, thanks so much for your attention to smoke and vulnerability. Can you say more about who you decided would be included in your co-production work? For example, how you decided on your survey sample frame?
Sure. So it was selective. And this work originally was born out of just communicating and scenario development with managers and practitioners. So there's not really a community outreach element to it, just to clarify that at first, but I think that's a next step of future work. And the management partners that we discussed really were kind of born out of organic phone conversations and me calling around and engaging with different individuals and being connected through, different colleagues of theirs. And so we started off with these organizational partners, and then the survey was then distributed to relevant individuals within that organization. So we don't have kind of our final sample frame of who would be responding to the survey just yet.
Thanks.
Sure thing.
Thanks, Maureen. Yeah, that's the only question I see in Huva.
Okay. Well, thank you, Kate, and thank you for all of our speakers for this session. I thought it was amazing. I think we covered a very wide range of different projects that are going on, that are still going on, even though the wildfires were 5 years ago, believe it or not. So there's a lot of really interesting things coming out of that. And yeah, thank you everybody for being here. Appreciate it.
All right. Thank you so much, Louise, and thanks to all of our speakers. Up next, we have a 20-minute break before our last set of breakouts begin. We have 2 special session breakouts, a general session and a safe meeting and trivia networking session, all beginning at 5 p.m. Eastern time. To choose the one you'd like to join, use the agenda tab on the left of your screen and click sessions. You can also click subsessions for more details about what to expect. And to join the session offering Spanish and Portuguese interpretation, be sure to select the session titled Actions for Sustaining Biodiversity in Fire-Prone Ecosystems. Thanks again to all of our speakers and enjoy the rest of your day.
Thank you, everybody.